Welcome to the deep dive. Today we're doing a really focused high-yield plunge into the kidneys. Specifically, we're looking at their structure and function based on Porth's Chapter 32. And it's just staggering when you consider the sheer scale. I mean, these two organs, maybe the size of your fist, they process something like 22 or 25% of all the blood your heart pumps out. That's 1,100 milliliters every single minute.
Which adds up to filtering about 180 liters of plasma every day. It's immense.
Wow.
So yeah, our mission today is really to understand how the physical setup of the kidney lets it do these two massive jobs. Filtering waste out of the blood, that's the excretory part, and also its endocrine roles controlling body fluid volume, blood pressure, things like that.
Okay, let's unpack this.
Yeah.
Starting with the basic architecture, the physical setup. So structure-wise, we've got the two kidneys bean-shaped, and they sit retroperitoneally. That means they're kind of tucked away behind the main abdominal cavity lining.
Exactly. And that little inward curve, the hilus, that's the main entry and exit point for the renal artery, the vein, nerves, and the ureter heading down to the bladder.
And if you were to slice one open, you'd see those two distinct zones.
The outer layer, the cortex, that's where the initial filtering units, the glomeruli, are. Then deeper in, you've got the medulla, which looks like it's made of these cone-shaped bits, the renal pyramids.
And separating those pyramids are extensions of the cortex, right? The renal columns.
Precisely. But the real workhorse, the fundamental unit doing the job, is the nephron.
Ah, yes, the nephron. Millions of them, aren't there?
Well, you start with about 800,000 to a million per kidney. But here's the really crucial, kind of sobering point. Your body can't make new nephrons.
It can.
Nope. And starting around age 40, you actually begin to lose them, maybe about 10% every decade, the ones that are left. They have to pick up the slack. They hypertrophy, basically get bigger to handle the load.
That has huge implications for kidney health as we age or with diseases. Okay, so the blood supply gets really specialized here.
It does. The main renal artery comes in and branches segmental interlobular arteries, and then the really important one for filtration, the afferent arteriole. That leads into the filtering unit.
Efferent means arriving.
Right. And what's fascinating is how the kidney controls where that blood goes. Normally, almost all of it floods the cortex, where the filters are. But let's say the body's under extreme stress, like in shock, losing a lot of fluid.
Yeah.
The kidney can actually shunt blood away from the cortex and redirect more of it towards the inner medulla.
But wouldn't that reduce filtration? Why do that?
It's a survival tactic. Less blood to the cortex does lower the filtration rate, which helps conserve precious body fluid. But directing flow to the medulla, that helps maintain the kidney's ability to concentrate urine, to hold on to water. It's prioritizing water balance over waste removal in a crisis.
Okay, that makes sense. Survival first.
Yeah.
And that ability to concentrate urine brings us to the nephrons themselves. You mentioned there are different types.
Yes, two main categories. About 85% are cortical nephrons. They mostly stay up in the cortex, have relatively short loops, the loop of Henle.
Okay.
But the other 15%, those are the juxtamedullary nephrons. They start deeper in the cortex, near the medulla, and crucially, they have these really long loops of Henle that dive way down into the medulla.
And those long loops are key for concentrating urine.
Exactly. They're essential for setting up the salt gradient that allows the kidney to pull water back later on.
Got it. So the journey starts at the filter of the glomerulus, famous for being a high-pressure zone.
It's unique. It's a capillary bed, but unlike others, it's sandwiched between two arterioles, the efferent bringing blood in and the efferent taking it out.
Okay, here's where it gets really interesting. Why is that pressure so high, like 60 millimeter Hg? That's way higher than a normal capillary.
Simple plumbing, really.
Yeah.
The afferent arteriole, the in-pipe, is wider than the efferent arteriole, the out-pipe.
Resistance.
Exactly. It's like slightly kinking the outflow hose. This resistance backs up the pressure inside the glomerular capillaries, and it's that high pressure, the hydrostatic pressure, that physically pushes fluid and small solutes out of the blood and into the first part of the nephron, Bowman's capsule.
So the pressure forces fluid out. But you need a barrier to keep the important stuff, like cells and big proteins, in the blood. Tell us about that filter.
It's a remarkable three-layer system. Think of it like a very sophisticated sieve. Layer 1. The capillary wall itself, endothelium, it has little holes, fenestrations.
Okay.
Layer 2, the basement membrane. This is a meshwork, no cells, but it's the main barrier based on size and electrical charge. It repels negatively charged things like most plasma proteins.
In layer 3.
That's made of specialized cells called podocytes. They have these foot processes that wrap around the capillaries, leaving little gaps between them called slit pores. That's the final check.
So fenestrations, basement membrane, slit pores. That complex system ensures big molecules, red blood cells, and especially plasma proteins normally stay out of the filtrate.
Correct. If proteins start showing up in the urine, that barrier is damaged. Oh, and we should mention the mesangial cells, too. They're kind of structural support cells within the glomerulus, but they can also contract to help regulate blood flow, and they're phagocytic. They clean up any debris.
Right, and the total amount of fluid filtered across this barrier every minute. That's the GFR, the glomerular filtration rate.
Yep. And that average number you hear is about 125 milliliters per minute, which, if you multiply it out, gives you that staggering 180 liters per day.
An enormous amount. But obviously we don't pee 180 liters a day. So that filtrate now enters the tubules for massive processing. This involves two key processes, reabsorption and secretion.
That's right. Reabsorption is pulling essential stuff back from the filtrate into the blood. Things like water, electrolytes, glucose, amino acids, stuff the body needs to keep.
And secretion.
Secretion is the opposite. It's actively transporting waste products or excess substances from the blood into the filtrate to be eliminated. Think of it as targeted disposal. And the efficiency is just incredible. Out of that 125 millilo filtered per minute, usually about 124 millilo gets reabsorbed.
Wow. So only about 1 ml actually becomes urine each minute. And this takes a lot of energy, right? Especially related to sodium.
Absolutely central. The real energy hog is the Ne+K plus AT-PACE pump. It sits on the side of the tubule cell facing away from the filtrate, the basolateral side. It's constantly pumping sodium out of the cell into the surrounding tissue fluid.
Why is that so important?
Because it keeps the sodium concentration inside the cell very low. This creates a steep gradient, a strong pull for sodium to move into the cell from the high sodium filtrate in the tubule.
Okay, a downhill run for sodium.
Exactly. And the cell harnesses the energy of that downhill sodium movement to pull other things along with it, even against their own concentration gradients. That's secondary active transport or co-transport. It's how glucose and amino acids get pulled back into the cell along with sodium.
Clever. And the first part of the tubule, the proximal tubule, seems to do most of this work.
It's the heavy lifter for sure. It reabsorbs about 65% of everything water, electrolytes like sodium and potassium, and pretty much all the valuable nutrients like glucose and amino acids, assuming levels are normal.
Which brings us to the idea of a transport maximum, or TM. What happens when there's just too much of something?
Well, those co-transporters, those carrier proteins, they have a limit. They can only work so fast. The TM is basically their saturation point. If the amount of a substance filtered into the tubule exceeds the capacity of its transporter,
It spills over.
exactly. The carriers are overwhelmed, and the excess stuff stays in the filtrate and ends up in the urine. The classic example is glucose in uncontrolled diabetes. Blood sugar gets so high that the amount filtered overwhelms the glucose transporters. Their TM is about 320 milligrams a minute. Once you exceed that renal threshold, glucose appears in the urine.
Makes sense. Okay, moving along the nephron to the loop of Henle, this is where that concentration gradient gets set up, right? The countercurrent system.
Yes, this is crucial for making concentrated urine. It works because the two limbs of the loop behave very differently towards water and salt.
How so?
Think of the descending limb going down into the salty medulla. It's highly permeable to water, but not very permeable to salt. So as the filtrate goes deeper into the salty environment, water is just pulled out by osmosis.
Okay, so the filtrate gets saltier as it goes down.
Right. Then it makes the hairpin turn and starts coming back up in the ascending limb. Now this limb is the opposite. It's practically impermeable to water, but it actively pumps salt, sodium potassium chloride, out of the filtrate into the surrounding medullary tissue.
So salt leaves, but water is trapped inside the tubule.
Exactly. This makes the filtrate become less concentrated, more dilute as it ascends. That's why the thick ascending limb is often called the diluting segment. And it's this pumping of salt out without water following that makes the medulla itself really salty, setting up the gradient.
And that active salt pump in the ascending limb, that's where some diuretics work.
Precisely. Powerful loop diuretics, like furosemide, target and block that specific Ne+K plus 2Cl cotransporter in the thick ascending limb. If you block salt reabsorption there, the salt stays in the filtrate, holds water with it, and leads to a massive increase in urine output.
Very effective. Okay, so after the loop, we're in the distal tubule and collecting duct. This is where the fine-tuning happens, largely under hormonal control.
Yes, final adjustments. Two key hormones here. First, ADH, antidiuretic hormone, also called vasopressin.
Triggered by dehydration or high blood saltiness.
Right, high plasma osmolality. ADH travels to the collecting ducts and makes them permeable to water. It does this by causing special water channels, aquaporin II, to be inserted into the cell membranes facing the filtrate. This allows water to leave the filtrate one last time, drawn out by that salty medulla, making the final urine concentrated.
So ADH basically opens the taps for water reabsorption. What about the second hormone?
That's aldosterone. Its main job is fine-tuning sodium and potassium balance. It acts on the principal cells, primarily in the late distal tubule and collecting duct.
What does it do there?
It stimulates the reabsorption of the last bit of sodium, and crucially, it promotes the secretion of potassium into the filtrate. It's the main way the body gets rid of excess potassium.
Got it. Okay, let's shift focus a bit to the overall regulation. You mentioned the kidney tries to keep its blood flow, RBF, and filtration rate, GFR, steady, even if our blood pressure fluctuates.
Yeah, that's called autoregulation. There are intrinsic mechanisms within the kidney, mainly involving the afferent arteriole constricting or dilating to maintain relatively constant flow and pressure despite changes in systemic arterial pressure, at least within a certain range.
But there's also a more complex feedback system, right? The juxtaglomerular complex, the JGC.
Yes, the GGC. This is a really elegant control center. It's physically located right where the distal tubule loops back and makes contact with the afferent arteriole, feeding its own glomerulus.
So the end of the tubule talks to the beginning of the filter.
In a way, yes. The specialized cells in the distal tubule wall at this contact point are called the macula densa. They act like sensors, monitoring the amount of sodium chloride salt flowing past them in the filtrate.
And the cells in the afferent arterial wall.
Those are the juxtaglomerular cells. They're the ones that actually synthesize and store renin.
Okay, so the macula densa senses low slow or low salt. What happens then?
It signals the juxtaglomerular cells to release renin into the bloodstream, and that kicks off the whole renin-angiotensin-aldosterone system, or RAA mechanism.
Let's trace that cascade. Renin acts on a precursor.
Angiotensinogen, made by the liver. Renin converts it to angiotensin I. Then, an enzyme called ACE, angiotensin-converting enzyme, mostly found in the lungs, converts angiotensin I to angiotensin II.
And angiotensin II is the really active player here.
Oh, yeah. It's a powerful vasoconstrictor, systemically raising blood pressure. It also directly stimulates the adrenal gland to release aldosterone, which we know saves sodium and water. But here's a critical kidney-specific action.
What's that?
Angiotensin II preferentially constricts the efferent arteriole, the one leaving the glomerulus.
The outflow pipe. Why is constricting that one so important?
Think about it. If your overall blood pressure is low, constricting the outflow helps to maintain the pressure inside the glomerulus. It prevents the filtration pressure from collapsing. It's a way to preserve GFR to keep the kidneys filtering, even when systemic perfusion is compromised. A vital survival mechanism.
Wow, that's clever design. Now, is there anything that counteracts this powerful RAA system?
Yes, thankfully. When the heart muscle gets stretched too much, say from high blood volume, the atria release atrial natriuretic peptide, or ANP.
Natriuretic meaning promoting sodium excretion.
Exactly. ANP basically opposes the RAA system. It promotes sodium and water excretion by the kidneys, it inhibits renin release, it inhibits aldosterone release, and it causes vasodilation. The net effect is to reduce blood volume and pressure, taking the strain off the heart.
A natural counterbalance.
Yeah.
Okay, beyond fluid and pressure, the kidneys are also the main long-term regulators of our body's pH, acid-base balance.
Critically important role. They do this primarily by reabsorbing filtered bicarbonate, HCO3, which is our main blood buffer, and by excreting excess hydrogen ions, H+.
But urine can only get so acidic, right?
Right. You can't just dump tons of free H+ into the urine. Its pH would plummet, stopping the process. So the kidneys use buffer systems within the tubule fluid to soak up those H+ ions. The main ones are the phosphate buffer system and, very importantly, ammonia, NH3, which combines with H+ to form ammonium, NH4+, trapping the acid for excretion.
Makes sense. And then there are the truly endocrine functions where the kidney actually produces hormones.
Two major ones. First, erythropoietin, or EPO. The kidney senses oxygen levels in the blood flowing through it. If it detects hypoxia, low oxygen, it releases EPO.
And EPO tells the bone marrow
to make more red blood cells. This is why chronic kidney failure almost always leads to anemia. The damaged kidneys can't produce enough EPO.
Okay. And the second hormone?
Vitamin D activation. We get vitamin D from diet or sunlight, and the liver converts it to an intermediate form. But it's the kidney that performs the final crucial step to convert it into the fully active form of vitamin D.
And active vitamin D is essential for?
Calcium absorption from the gut and overall calcium and bone health. Again, in kidney failure, this activation step falters, contributing to bone disease.
So much going on. Okay, now that we understand the machinery, how do we actually measure how well it's working in a clinical setting? Let's start with renal clearance.
Renal clearance is a concept that tells us how effectively the kidneys are clearing a substance from the blood plasma. The formal calculation is C equals UVP, concentration in urine times urine flow rate, divided by plasma concentration.
What does it mean?
It represents the theoretical volume of plasma that is completely emptied of that substance each minute. A high clearance means the kidney is getting rid of it fast. Low clearance means it's building up in the blood.
Okay, and for simpler urine tests, specific gravity.
Yeah, specific gravity is a quick measure of urine concentration, basically comparing its density to pure water. The normal range is usually like 1.005 to 1.025. It tells you about hydration status and, importantly, the kidney's ability to concentrate urine.
What if it's low?
If the kidney loses its concentrating ability, which is often an early sign of damage, the specific gravity gets stuck at a low, fixed level, maybe around 1.006 to 1.010, regardless of hydration.
And checking for protein in the urine? Proteinuria.
That's a key indicator of glomerular damage, since that filter should normally keep proteins out. We often specifically test for microalbuminuria.
Why micro and why albumin?
Albumin is the smallest major plasma protein, so it's usually the first to leak through if the filter starts to fail. Detecting small amounts, micro levels, technically over 30 milligrams per day, can pick up damage much earlier than waiting for larger amounts of protein or clinical proteinuria to show up. It's an early warning sign, especially in diabetes.
Makes sense. Now, for blood tests, the big one is serum creatinine.
Definitely. Creatinine is probably our best simple blood marker for GFR. Why? Because it's produced by muscle metabolism at a pretty constant rate. It's freely filtered by the glomeruli, and it's hardly touched by the tubules' minimal secretion or reabsorption.
So its level in the blood directly reflects how well the kidneys are filtering it out.
Pretty much. If GFR goes down, creatinine isn't cleared as effectively, and its level in the blood goes up. And here's a crucial clinical rule of thumb. If a patient's serum creatinine triples from their baseline, it generally implies they've lost about 75% of their kidney function. It's a nonlinear relationship, so small rises at first mean more than you'd think, and later rises signify massive functional loss.
That's a sobering benchmark. How does that compare to blood urea nitrogen, or BUN?
BUN measures urea, the end product of protein metabolism. It's also related to GFR. If GFR drops, BUN usually rises, but BUN is way more variable than creatinine.
Why is that?
Because BUN levels are affected by things other than just kidney function, like how much protein you eat, whether you have tissue breakdown, like from trauma or steroids, and very much by hydration status. If you're dehydrated, BUN goes up significantly because more urea gets passively reabsorbed along with water.
So creatinine is a cleaner marker of GFR itself.
Generally, yes, but the ratio of BUN to creatinine is diagnostically useful. Normally, it's about 10.1. If the ratio climbs much higher, say 15.1 or 20.1, it often suggests a prerenal cause, meaning the problem is before the kidney, like dehydration or poor blood flow rather than intrinsic kidney damage itself.
Useful distinction. And finally, imaging. How do we visualize the kidneys?
Imaging helps us see the structure. Ultrasound is often the first step. It's non-invasive, uses sound waves, and it's great for telling the difference between fluid-filled things like cysts and solid masses like tumors.
What about tests using dye?
Historically, there was the IVP, or excretory urography. You inject a radiopaque dye that gets filtered by the kidneys, and then take x-rays to watch it move through the collecting system, outlining the structures. Nowadays, CT scans and MRIs give much more detailed anatomical pictures, and angiography specifically looks at the blood vessels. So pulling it all together, we've seen the kidney is just this incredible piece of biological engineering. You've got the high-pressure filtration up front, then this massive, energy-intensive process of selective reabsorption and secretion in the tubules, all governed by these intricate feedback loops and hormones like the RAA system for survival, AMP for balance, EPO for blood cells, vitamin D for bones.
Yeah, it really paints a picture of interconnectedness. What this all means, I think, is that the kidney isn't just a filter. It's a central regulator. If one part of the system gets hit, maybe GFR drops because of low blood pressure. The knock-on effects ripple through everything. Fluid balance, electrolytes, acid-base status, even red blood cell counts, because it's all linked through mechanisms like the RAA system. And just as a final thought for you listeners to maybe chew on, remember we talked about active secretion in the proximal tubule? how the kidney uses specific transporters to dump waste products, organic ions, into the filtrate.
Yeah, getting rid of metabolic byproducts and toxins.
Well, think about common drugs, things like penicillin, certain diuretics, even high doses of aspirin. Many of these are also organic anions. They actually compete for the very same secretory transporters that the body uses to get rid of natural waste like uric acid.
Ah, so taking those drugs can essentially cause a traffic jam at the transporter level.
Exactly. It can potentially slow down the excretion of uric acid, which is clinically relevant because that could worsen conditions like gout in susceptible people. It just highlights how profoundly medications can interact with these fundamental physiological pathways in the kidney, affecting more than just their own elimination. Something to think about.